Okay, here's a third example of using the method of joints to analyze a truss. Okay, this truss is more complicated. There's more than just three members, and sometimes when that happens, you're going to need to use the support structure of the truss to write some equilibrium equations to help you find extra things that you know so that you can apply the method of joints. Okay, so for example, let's get started. If we were looking at this, I think the hint that we've been working on is look for members that join together where there's only two unknowns. Okay, so I see this, let me highlight it here at joint A. At joint A, there's only two unknowns, right? FAB and FAD. And in fact, we can quickly look at joint A. Here's something coming down. The force 7K is coming down. And then FAB working into the joint, assuming compression. FAD into the joint, assuming compression. Well, if you look at this, sum of forces in the x direction, there's only FAB working in the x direction. There's no opposing force. And so that tells you that FAB is 0. Okay, so that's a special case. This is a member of a truss that's carrying no load for this particular loading condition. Okay, so your first inclination when you see that is to think, well, does that mean I can take that member out? And I think it's obvious that truss would collapse if we took that member out. So just because the zero force member doesn't mean it's not needed. Plus, if I change the loading condition, you know, if I move this load to work at an angle, then it's going to have some force distributed through that member. Okay, so I wanted to show you an example where there's a zero force member in a problem, just so that you know that that can come up. Okay, so FAB is 0. All right, then we look, okay, if I know that, I can find FAD, right? I'm going to drop the F, okay, because it gets cumbersome to write that. So the member force AB is 0. The member force AD is going to be 7K, right, because it has to oppose the load. All right, I didn't write that very neatly. So 7K. And because that's positive, this would be kilonewtons. Because it's positive, it is in compression like we assumed. Okay, so we've immediately found two of these, all right? But then when I start to look at joint D, I'm going to have the force, the supporting force from the roller in the vertical direction. And then I'm going to have this force working into the pin from member DB. And then I know AD. Okay, so FAD working in compression goes here. And then I have yet another member right here that is, I didn't label that point, that's DE. Okay, so I'm looking at this, I know AD, I don't know D, I don't know DE, and I don't know DB. Okay, so I highlighted those in yellow, so let me put the things that I don't know in a different color. Okay, so I don't know these forces. So I would move on, okay? And if you carefully look at all the other nodes, you know, there's well, first of all, hopefully you can see some symmetry. If we solve for the left half of the truss forces, the same answers are going to apply in the right half just because this is symmetrically loaded, okay? But let's talk about that in a second. All right, so I'm a little bit stuck if I'm just wanting to look at the method of joints to keep going with this problem. All right, so that's what happens in many cases where you're going to have to take a look at the overall free body diagram to come up with the reaction forces at the supports. Okay, so I can actually solve for D here and the reaction force at the pin roller at F. Okay, all right, so let's do that. Let's get you started with that. Okay, and I'm going to draw a free body diagram of the rectangular shape. And at this point, I don't really care that the structure is made out of truss members. I'm just trying to get an idea of the reaction forces. So this shape is supposed to represent the free body diagram of the overall structure. And what I know is that I have a reaction force in the vertical direction. I'm going to call that D. Then I have reaction forces at point F, Fy, and Fx. Okay, it's a pin, so it's got two forces. All right, and then I have all these external forces operating. Okay, so I know 8K comes down. I know 7K, 24K in the center, and another 7K. And scoot this down a little bit. Okay, so this is a static equilibrium problem like we did last week. Okay, so we can do sum of forces in the x direction, and when we do that, we get that Fx is equal to 0. Easy enough. Now we can do sum of forces in the y direction, and when we do that, we get that D is moving up plus Fy, which is also moving up, is equal to all the stuff that's moving down. So 7K plus 8K plus 7K plus 24K. So there's another equation. But that's just one equation, and we still don't know D and we don't know Fy. Okay, so what would we do? Well, what we did last week was we took a look at the sum of moments. All right, and we could choose any point. The point I'm going to choose is this point F. All right, if I choose point F, then Fx and Fy drop out of the problem. Okay, so choosing those points, I can calculate the moment. All right, so this is 1.5 away. So this moment arm out to the 8K is 1.5 times 8. All right, and that causes counterclockwise motion. So writing sum of moments, I get 1.5 times 8. All right, and then this 7K goes directly through the point, so there's no moment generated, no rotation generated by that upper right corner 7K force. All right, then I have plus 24K. All right, and that moment arm is also 1.5, and it also causes counterclockwise rotation. So this would be a plus 1.5 times 24K. All right, then I have 7K, and the moment arm to the 7K force, this 7K, is 3. Okay, so 3 times 7K. All right, and so that one's also generating counterclockwise rotation. All right, so I think I've taken care of all of them. I took this one, it's right here. This one is right here. This one doesn't matter because it goes through the line of action goes through the point that I'm writing the moment around. And then 8K. All right, so I've taken care of the rotational forces, but then I have minus, this force D causes a clockwise rotation, so it would be minus D times that moment arm, which is 3, equal to 0. Okay, so from that I can solve for D, and I think I get D in that case is 69, these things add up to 69K divided by 3, which is 23K. All right, so there's this force D. All right, so what that gives me, what that lets me do, is now I can consider joint D. At joint D, I know I have this 23K force because I just calculated that. I know I have the member force. I'm going to put this joint going into the joint because I assume it's in compression. Actually, I'd already calculated that it was in compression. I know that value is 7K. All right, and then I have up here member DB, and I can put that in compression. Okay, and I can use this to solve for DB. Okay, so what I'm going to need is the angles. All right, so here's the angle theta, and from the problem I can see that theta is going to be an arctan of rise 0.8 over run 1.5. So theta is arctan rise over run. Okay, just double checking I got the numbers right. Okay, so what that lets me do is I forgot a force. I forgot an angle. You know, it was bothering me because there was no opposing, or there's no x direction force other than dB. Okay, so I forgot. You look at this. I forgot dE. dE moves this way. Okay, so I have this force dE. Okay, now I can write some of forces in the x direction. So that gives me dE with a minus sign because it's moving back to the left. Okay, minus dB cosine of theta. Theta is known. Okay, when you sum those up, that's equal to 0. Okay, and then you can write one more equation. Minus 7K, this was sum of forces in the x direction, the first equation. Sum of forces in the y direction is minus 7K plus 23K plus dE. I'm sorry, there's no dE because that's the vertical direction. Plus dB sine of theta is equal to 0. Okay, actually, you see what I did there? I missed the sign. dB works down, so this would be a minus. Okay, so from there I can solve for dB. These numbers add up to, let's see, 16K. All right, so dB is equal to 16K over sine theta, which is 34K. All right, that was a positive number. I assumed it was in compression, so dB is 34K in compression. Okay, so that gives me one other force that I've known, and so from there, I now know this. I know this is a 0 force member. Okay, and I know I can solve for dE as well because I have this equation. Okay, so I'm well on my way to solving for the rest of the force members. So I'm going to leave the rest of that as part of the quiz for this video to figure out the other forces involved. So you'll have to, take your time and work through that and get the answers for this video quiz.